Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is graph bipartite. I would say this is less of a problem and more of a graph concept. They have directly asked us because I would say it's one of the most important concept of graph. So we will understand the concept and then also we will solve this problem, which is very much aligned. So there is an undirected graph with n nodes where each node is numbered from 0 to n minus 1. Now you are given a 2D array called graph, where graph at the ith position, uth position, is an array of nodes that u is adjacent to or connected to. More formally, for each v in graph u, there is an undirected edge between u and v. The graph has following properties. There are no self edges, so there is no self edge, does not contain u. So the one node is not connected to itself. That's what they have tried to say. So at position u in graph, there won't be u itself, all right, at the uth index. There are no parallel edges, so does not contain duplicate values. If v is in graph u, then u is in graph v. Makes sense because it's undirected. The graph may not be connected, meaning there may be two nodes u and v such that there is no path between them. Of course, some graph some nodes might not be connected at all, right? And there might be it's not even the entire graph is not like connected component as well, because there might be multiple connected components of this graph. So we have to consider every scenario here. And now we have to return if and only if this graph is bipartite. All right, so let's dive deep into solving this problem. But before, so these are the examples we will be solving, understanding the concept. But before we come on here, I want to start this video with understanding what is a bipartite graph. Let me tell you, this is one of the most asked concept from graph, because it just like plugs into like multiple problems so well. Most of the time the problem will be asking you like group nodes like into separate groups, and then they might be asking you to assign like multiple colors or two different colors. Well, here in bipartite, we need to focus on these two, bi and partite. So bi means two, partite means two groups or parts. So this means bipartite means, can you group all these nodes into two groups such that no two adjacent nodes are in the same group? That's all. And can you do that? If you can do that, that means the graph is bipartite, otherwise not. So this example that I have taken here, we have 6 nodes. 0, 1, 2, 3, 4, 5. So if you see here, and we can even write the graph for it. So this graph will be, so at each node, so 0 is connected to, we can say is connected to 1. 1 is connected, or we can say it like this, and 1 is connected to 0, and then 2. Then 2 is connected to 4. Well, before that it's connected to 1, and we are not connecting the same node to itself. Okay, so that's not an issue. And then what is 3 connected to? 4. What is 4 connected to? 3 and 5. So I think we have covered all the nodes. So 0, this is 1, this is 2, this is 3, this is 4, and I think we forgot about 5, because 5 is connected to just 4. So I will add 5 as well here. So 5 is connected to just 4. All right, so now we are complete, and this is 5th node. Now these are basically the neighbors or connected members of each of these nodes, right? Okay, all right. So this particular graph that we are given here, is it bipartite? So bipartite means grouping it into two sets. So an easier way would be, can you assign two different colors to the nodes given that no two adjacent nodes are same colors? So I can say that here there will be basically set 1, and then set 2. Can we group these nodes into two separate groups, two separate sets, such that no two adjacent nodes are in the same set? And we will do the coloring as well at the same time. So let's say I choose two colors, red and blue. Red and blue, these are the two. Or maybe let's not choose this one, let's choose this one. So red and blue, I'm calling violet blue color. So these are the two different colors that we have chosen. So what we'll do, we'll start with one of the colors randomly. Let's start with red color and assign our 0 red color. So we have assigned 0 red color, so it's in set 1. So 0 is in set 1. How about next connected member of 0? So we are running DFS on it, by the way. We are running DFS. So we'll be running DFS on the neighbor of, we're running it on 0, and then we are exploring its neighbors. So since we assigned red already to 0, its neighbor, any neighbor that's connected to, they will all have opposite color. All right. So here, our next node right here, 1, is going to go into different set, and we'll assign the color violet to it. All right, and we'll also put it into different set. Now, how about the members that 1 is connected to? What are the neighbors of 1? Well, 0 was a neighbor, but it's already been visited. Its color is already been assigned, so we're not going to visit that again. But next color need to be flipped. It has to become red. So this one will be assigned basically red, and it needs to be put into the group set 1. So 2. Then what are the neighbors of 2? 2's neighbors is 4. So then we'll flip the color this time. 4 will be added to set 2. Then what about neighbors of 4? 4 neighbor is 5 and 3, because these are two neighbors simultaneously need to be assigned the color, or just one by one, but they both need to be assigned the same color, and that has to be in opposite of the color that we just assigned to 4. Well, the good thing is these two nodes, they are not connected, so we can actually assign them the same color. So we can assign them red, color, and we can put both of these nodes into basically our set 1. Well, congratulations, this graph is bipartite. This graph is bipartite because we were able to group all these nodes into two different sets, or assign two different colors, such that no two neighboring colors, so these two do not have same colors, these two do not have same colors, these two do not have same colors, and these two do not have same colors. So no two connected or adjacent nodes have same colors, or they are in two different sets. Now let's understand when this graph would not be a bipartite graph. Well, okay, so there might be certain scenarios. Let me tell you that whenever the graph does not have a cycle, it's always going to be bipartite, because you will always end up in a situation where you can flip the colors as you are moving in a non-cyclic graph. But if you introduce a cycle, it's not always the case that it's going to be not bipartite. Let me show you how. So if I introduce a cycle right here, let's say if I connect these two, then what do you see? You see that two neighbors of this graph have the same color. like these two, if these two become neighbors, then we have two adjacent nodes that are the same color. That means that is not going to be bipartite, because we can't put these two into the different set because they are the same colors, right? But what if instead of that I was introducing a cycle like here, now you can actually, because these two nodes are of different colors. So what is the difference between introducing this cycle, and this cycle? Don't you see that this cycle has 3 members? So that means this has odd number of members, odd number of nodes. But this one, this right here, this right here has even number of members. So even number of members. So that means whenever there are even number of nodes in the cycle, if there is a cycle, then you can always call that or assign, put all the nodes of that graph into 2 different sets or assign 2 different colors. So that is a bipartite graph. But because whenever there is a cycle and in the cycle there are odd number of nodes, then you will always end up in a situation where like you are kind of assigning like 2 different 2 same colors, the same set. So that will not be possible because 2 neighboring nodes cannot have the same color, because that will violate the definition of the bipartite graph. Now you can see right here in the second case as well, like if I introduce a cycle here, and now we have basically 1, 2, 3, 4 and 5 members in the cycle, then also it's not possible because we were in a situation where we were joining together 2 nodes that are the same color. All right, so now we understand the concept very well. So it's just all about running the DFS and assigning colors, and at the same time through this you can also find the cycle in the graph, because if you try to assign you cannot find the cycle, but I would say like odd number of nodes in a cycle, so that could be a potential problem, right? So let's write down the code. It will be super simple. It will be just running a DFS. So what we'll do is we'll have a colors. So let me I shouldn't have, okay, these 2 colors we can number them. It's better to work with numbers. So we can call this red 0, and then we can call this violet color 1, and then we can make colors array that is going to be of same size, initially containing just -1 value. That means we have not assigned any color to any node. So we have 6 nodes, so basically 6 -1s. And then we will be basically calling a for loop. That for loop will be visiting each node. So for node in our graph, or we can say range graph. So in range length graph. So that will, because the graph could be disconnected as well. So it's not possible you just run DFS on 0 and you're able to visit all the nodes. So in this case, if in my colors, that means I have not visited it. So if this node, basically it's the index, is equals to -1, then only I would want to visit it. So I'll just call DFS on it with node and next color. So next color would be, what will be the next color? Let's start with 0, because this is the first we will be calling in this disconnected graph, or this connected graph but like just one graph. And if this is, so if DFS here is false, then we can return false. This is not a bipartite graph, or we return true in the end. But let's now write this DFS right here. It will be quite short, so we'll just say DFS. It will be taking node and then next color, so I'll call it next color. So here to the node I can assign the color. So in the colors, this node, and by the way I'm calling it on a non-visited vertex, so that's why I can safely assign the color here. Otherwise I will basically try to explore all the neighbors of, so I'm gonna call it neighbors, or maybe V is a better term, so V, and I should have called this U. So this is U, this is V in graph U, at U. So this will give me all the neighbors of this. So if this V is not -1, that means if the colors at V is equals to next color, that means it's already visited and it's the same color that I need to assign. You know, it's the same color that U is already assigned, and I'm exploring the neighbor of U, and they cannot have same color, so I can return safely false. So return false. Otherwise, else would be you need to assign the color, but like only if it's not already -1. So if colors of this neighbor, so V is equals to -1, then we can call DFS on it. So if DFS on V and next color would be 1 minus, we can do 1 minus next color. And let me tell you why am I doing this. Next color, let me move this code like a little bit here. Okay, so you can see. Yeah, so if 1 minus next color, and the reason is that if last color was 0, so 1 minus 0 would be 1. If last color was 1, so 1 minus 1 would be 0. So we are just flipping the color, all right, without even like thinking much about it. So, and then we can return false. Otherwise, in the end, you can return true. Return true. All right. So we have already understood what a bipartite graph is. Here it will be like super simple. So it's all about assigning two different colors, or putting all the nodes into two different sets, such that no two neighboring nodes are in the same set, or they are assigned the same color. So let's consider our first example and see like why this one is not a bipartite graph. So here you can see this node 0 is connected to 1 through 3, 1 is connected to 0 and 2, 2 is connected to 0, 1, 3, and 3 is connected to 0 and 2. Now if you see, let's start with, so these are the two colors we can assign, so red and violet. So these are the two colors we can assign. So let's start with 0th node, and I assign it 0. Let's assign it nicely. So I assign it red, and then I'm gonna start visiting its neighbors. So all the neighbors that it has is 1, 3, and 2. So now I will be assigning violet to all the neighbors it has. So I'll assign violet to 1 and then 3. Now and then I will have to assign violet to 2 as well, But if you see right here, this is already not a bipartite graph because these two neighbors are being assigned the same colors and they are connected to each other. Basically, these are adjacent nodes. So this is not a bipartite graph. So what we'll be doing is we'll be calling DFS on all the nodes, and if in my colors set that I've already explained in the previous part, so in my colors so initially it will be all -1. So this has 4 nodes, and then if so here, let's say we start visiting 0, and because this is the first node, I can assign it 0 or red color, we can say red color, and then I'm visiting all its neighbors, and then I'm assigning basically violet color to them. So I assign violet here, then assign violet here, and then I assign violet to 3 as well. But when I start visiting 3 again, I see that its neighbor 2 is already visited and its color is actually the same color, that's color of 3. So that is why I will return false from there. So return false. Now let's get to the second example, why this one is. And also, if you remember, we were talking about the cycle, and this one actually this first example does have a cycle that is of odd length. So if you see right here, this is the cycle between 0, 1 and 2, and this has odd length. So that is why this is not a bipartite graph. Well, this one is also, this second example does have cycle, but this one has basically even number of nodes in the cycle. So that is why this is a bipartite graph. But we can again, have all the same coloring applied to it. So we'll have colors initially all -1, all -1. I can use the previous. So I'll have colors all -1, and then there are 4 nodes, so we'll have them assigned. So red is, let's say red is 0 and violet is 1. Now we can assign the colors. Okay, so let's run DFS on the second example. So I will start with 0. So I'll assign this color red, or you can say 1, and I will change that to 1 in the code. Now I will explore neighbors of 1 since we are running DFS. So I'll go visit 1, and then I will assign this opposite color, which is violet, or we can call 1. So I will change this to 1. Sorry, this was 0, my bad. This was 0, and this is gonna be 1. Now let's explore the neighbor of 1, which is 2. 0 is already visited, so we're not gonna go there. So this will be assigned color red, and we've done that successfully. So this will be assigned 0, and then in the neighbors of 2 we have 3. So here in 3 will be basically flipping the color and assigning it violet, or this one as 1. Now you see we were successfully able to group these nodes, all of them, into 2 different sets, such that no 2 groups are basically connected together if they belong to 2 different colors. So now let's just write the code for it, and I hope you have already been through this. I think we'll be writing most of the code just like this. All right, so let's convert our pseudocode into actual code. You can see it nicely. So I'll just have colors array of initially everything -1 into length graph. Then what I'll do is basically I'll visit all the nodes. So for, I can say node in graph, or maybe range graph, because graph is more is like list of list where each index has all the neighbors that it's supposed to have. Those might be empty, it might be a disconnected graph, but that is why we are trying to visit all the nodes in the graph. Otherwise we would have just called DFS on just 0th node if it was like entirely connected. So if this node, so if colors at this index is actually -1, that's when we can call the DFS on it. And if this DFS returns false, so at this node, and we're going to send in the next color, which is going to be 0, that's our starting color. We're going to assign just two colors here. I can just mention that we can say red is going to be 0, and then blue is going to be 1. Now, so if this is returning me false, then I can just return false. Otherwise, we have traversed all the graph, we assigned all of them right color, so we can return true in the end. Let's write down the DFS. So DFS will be taking the node. I'm gonna call it U, and then next color. So next color. This next color, since I'm already calling this on an unvisited graph, so, unvisited vertex, so I can just assign the color directly here. So in my colors, U can be changed to next color. Let's visit all its neighbors. So for V in graph U, if this V is already visited, that means it's not equals to -1, which also means in colors V is going to be equals to this next color or something else. But if it is equals to next color, that means we need to return false, because this is the color that I've just assigned to U, and V is the neighbor of U, then we cannot assign it the same color. So that means we are assigning the color to U, which is connected to V, and V already has that color. So that means the graph is not bipartite, so we'll return false. Otherwise, another scenario is if basically this V is actually not visited. So if this is not visited, it's not equals to, or you can say it's equals to -1, that means it's not visited, then I can call DFS on it, and if this DFS returns false, then I can return false. Otherwise, in the end, I can just return true. So I'm sending in V, and then 1 minus next color, as we have discussed, because if the next color, current color is you know what, yeah, but I think this makes more sense. Next color here makes more sense. So, or maybe current color makes more sense. So I'm assigning the current color. So current color, and if this current color, if you are trying to basically find the next color, it can be, if current color is 0, so 1 minus 0 would be 1. So next time we need to flip the color, so now it's going to be 1, not 0. But if it was 1, then 1 minus 1 would be 0. So that's a smart way of flipping between 1 and 0. So we can just say current color, and if this is false, then we can return false. Otherwise, in the end, we can just return true right here. Okay, so let's zoom out and run it on our example cases. Okay, this is, yeah, of course, come on. This is going to be the length. Awesome, so this runs, let's submit it. I'm gonna clean it up a little. So it's a nice code with good time complexity. Let's write down the time complexity for this. Time complexity is going to be big of, so there are n number of nodes, and we are visiting just that number of nodes, so it's going to be v plus e because we are using the edges as well. And then for space complexity as well, it's going to be same, so it's going to be v plus e. So let's go back to AlgoYogi, mark this solved. See you guys later in the next problem.